March 1930, Manhattan. The engineering calculations spread across Heinrich Müller's drafting table would determine whether American construction methods could survive professional scrutiny. European-trained structural engineers examining the Empire State blueprints discovered numbers that challenged everything their Berlin academies had taught them about proper steel construction. 1,575,100 individual hot rivet connections, 18 months to complete. Four-man crews working 1,000 feet above Fifth Avenue in winter conditions. Through the coal smoke and pneumatic hammer noise of the construction site, American workers were attempting something European engineering declared impossible. Not just building the world's tallest structure, but proving that red-hot rivets driven by immigrant crews could create connections superior to modern bolted steel. In European construction, precision meant controlled shop conditions, unlimited time, sophisticated bolt technology. The Americans were operating with industrial philosophy the Europeans considered primitive. Portable coal forges balanced on steel beams. Red-hot rivets tossed 25 feet through open air. Installation timing measured in seconds, not hours. Connection strength that increased as each rivet cooled and contracted. 1,200 miles from European engineering schools, the most decisive construction revolution in structural history was revealing itself, not in superior calculations, not in advanced materials, but in the marriage of immigrant craftsmanship and American industrial coordination that would create joints lasting 93 years, while modern bolted skyscrapers require constant maintenance. Heinrich Müller adjusted his wire-rimmed spectacles and spread the Empire State Building blueprints across the mahogany conference table at American Bridge Company's Manhattan offices. The March morning light streaming through the windows illuminated engineering drawings that defied every principle he had learned during 15 years of steel construction in Berlin. Müller ran his finger along the structural specifications, calculating connection requirements with the methodical precision that had made him chief consulting engineer for 3 major European construction firms. "Gentlemen," Müller announced to the assembled American contractors, his German accent lending gravity to each syllable, "these numbers represent an engineering impossibility." He tapped the blueprint with his mechanical pencil. 1,575,100 individual rivet connections. Your proposed schedule allows 18 months for completion. In proper European construction, we calculate 6 rivets per man per day under controlled shop conditions. His voice carried the authority of someone who had overseen the construction of Berlin's most prestigious steel structures. This American schedule demands 12 rivets per man per day in open-air conditions at heights exceeding 1,000 feet through New York winter weather. William Sterrett leaned back in his leather chair, studying the German engineer with the calculating gaze of a man who had built his reputation on achieving the impossible. At 52, Sterrett had transformed Sterrett Brothers and Eakin into America's premier skyscraper construction company through what competitors called American audacity and what he preferred to term operational innovation. The company had erected more steel above the 30-story mark than any firm in the world, developing techniques that European engineering schools refused to acknowledge in their curricula. "Dr. Müller," Sterrett replied, his voice carrying the confident tone of someone accustomed to converting skeptics into believers, "your European calculations assume traditional methods. We're not building according to German engineering textbooks." He stood and walked to the window overlooking Fifth Avenue, where horse-drawn carts shared the street with Pierce Arrow automobiles, symbols of an America caught between old-world craftsmanship and new-world mechanization. American construction succeeds through coordination, not just calculation. Our 4-man rivet crews operate like precision machines. Starrett began describing the system that had made his company legendary among New York contractors. Each rivet crew functioned as a choreographed unit, the heater tending a portable coal forge balanced on wooden planks stretched between steel beams, maintaining constant temperature at exactly 1,700 degrees Fahrenheit. The catcher positioned 25 feet away, leather mitts protecting his hands as he snagged red-hot rivets thrown through open air with accuracy that amazed even veteran steelworkers. the bucker-up working from the opposite side of the connection, holding each rivet steady with a steel backing bar while his partner, the gunman, drove it home using a 30-pound pneumatic hammer that generated enough force to mushroom the rivet head in 15 seconds. "We're not just building a skyscraper," Starrett continued, turning back to face Mueller and the other assembled engineers. "We're proving that American industrial organization can achieve what European engineering considers impossible through the marriage of immigrant skill and American innovation." Mueller opened his leather-bound reference manual, pages filled with stress calculations and safety factors developed by the German Institute for Steel Construction. "Mr. Starrett, enthusiasm cannot overcome physics. Your proposed schedule requires installation rates that exceed human capability. Consider the Eiffel Tower, 2.5 million rivets, but constructed with unlimited time under controlled conditions, with each connection completed in workshop environments before field assembly." The fundamental disagreement that would define the entire Empire State Project crystallized in that moment. European engineering emphasized theoretical perfection, extensive planning, controlled conditions, and methodical execution that prioritized safety margins over speed. American construction culture had evolved differently, driven by urban real estate pressures and immigrant labor forces willing to attempt techniques that European craftsmen considered reckless. By April, reality began testing Starrett's confidence. The first steel shipments arrived from Carnegie's Pittsburgh mills, some beams still radiating heat from the furnaces, but rivet installation immediately fell behind projected schedules. Mueller's predictions seemed vindicated as crews struggled with wind conditions that scattered red-hot rivets across Fifth Avenue, forcing police to establish safety perimeters around the construction site. Workers experienced altitude sickness at heights where European regulations prohibited construction activity. Insurance companies calculated failure probabilities that made underwriters nervous about American construction methods. The engineering establishment mobilized its criticism through professional journals and international conferences. The British Institution of Structural Engineers published a formal analysis calling the Empire State Project "American bravado exceeding engineering prudence." German steel manufacturers offered to supply scientifically superior, high-strength bolts as alternatives to what they termed primitive hot rivet technology. Even Carnegie Steel executives, despite their materials supply contracts, privately worried that project failure would discredit American construction methods throughout the international engineering community. By May, with steel erection reaching only the 15th floor, doubt had infected the entire project. Starrett's rivet crews were averaging 8 connections per man per day, superior to European rates, but insufficient for the ambitious schedule that had made the Empire State Building a symbol of American industrial capability. Mueller and his European colleagues prepared statements explaining why American haste had inevitably resulted in project failure, validating their conservative approach to major construction projects. The crisis deepened when New York building inspectors, responding to European engineering criticism, began requiring additional safety inspections that further slowed construction progress. Weather delays compounded scheduling problems as spring storms made high-altitude work impossible for days at a time. The financial pressure intensified as investors watched European engineering predictions apparently proven correct through American operational failure. Standing on the 15th floor as evening shadows stretched across Manhattan, Starrett recognized that conventional approaches had failed. The project's success would require an unprecedented integration of American organizational innovation, immigrant craftsman expertise, and industrial coordination that transcended traditional construction methods. Only by perfecting hot rivet technology beyond anything previously achieved could the Empire State Building prove that American engineering represented evolution rather than reckless experimentation, setting the stage for a construction revolution that would redefine what the world considered possible in structural engineering. John Bowser arrived at the Empire State construction site before dawn on June 1st, carrying the detailed operational charts that would transform chaos into precision. The Canadian-born superintendent had spent 3 weeks analyzing every failed rivet installation, timing each crew member's movements, and calculating the mathematical relationships between forge temperature, throwing accuracy, and installation speed. His breakthrough came not from rejecting American methods, but from perfecting them through systematic coordination that treated human skill as the foundation for industrial innovation. Instead of scattered individual crews working independently across the steel framework, Bowser implemented what he called rivet assembly lines, synchronized teams following the structural steel erection by exactly 3 floors, creating a rhythm that transformed the construction site into a vertical factory. Each crew would handle precisely 150 rivets per day through choreographed movements that eliminated wasted motion and maximized the thermal window during which red-hot steel remained workable. The revolution began at 5:30 each morning, when the heater, typically an Irish or Italian immigrant with years of forge experience, lit the portable coal furnace and began the delicate process of calibrating temperature. The coal had to burn cleanly enough to avoid contaminating the steel while generating the 1700-degree heat that made rivets malleable. Too cool, and the rivet would resist deformation, creating weak connections. Too hot, and the steel would burn, compromising its structural integrity. The heater's expertise lay in reading the subtle color variations that indicated perfect temperature, cherry red with just enough orange to signal optimal malleability. At exactly 6 o'clock, the first rivet sailed through 25 feet of open air in a perfect parabolic arc, calculated by the thrower's unconscious mastery of physics. Pat McGrath, the legendary Irish catcher whose reputation had spread throughout Manhattan's construction community, positioned himself with the focused intensity of a baseball player tracking a fly ball. His leather-lined bucket, specially designed to absorb the rivet's kinetic energy without damaging the red-hot steel, caught the projectile with a precision that amazed even veteran steelworkers. Within 15 seconds of leaving the forge, the rivet was positioned in its designated hole, ready for installation. The bucker-up, working from the interior side of the connection, pressed his steel backing bar against the rivet head with exactly enough pressure to prevent movement without interfering with the pneumatic gun's operation. Carlo Benedetto, whose family had operated blacksmith shops in Milan for 3 generations, brought an intuitive understanding of steel behavior that allowed him to judge the optimal installation moment by subtle changes in the rivet's color and texture. His ability to reject pieces that were 50 degrees off target with visual accuracy matching expensive scientific instruments represented the marriage of traditional craftsmanship and industrial precision. The gunman completed the installation using a 30-pound pneumatic hammer that delivered controlled bursts of compressed air, mushrooming the rivet head while avoiding the excessive force that could damage surrounding steel. The entire process, from forge to finished connection, required exactly 45 seconds when performed by experienced crews working in perfect coordination. Bowser's innovation lay in recognizing that this timing could be systematized across multiple crews working simultaneously, creating installation rates that European engineers considered physically impossible. The physics underlying hot rivet superiority became apparent as each connection cooled. Unlike bolts, which were installed at ambient temperature and relied solely on threading tension, hot rivets contracted as they lost heat, generating 30,000 pounds of clamping force that squeezed steel plates together with molecular-level intimacy. This thermal contraction created bearing contact across 100% of the joint surface, eliminating the microscopic gaps that allowed bolt connections to loosen under building vibration and thermal expansion. European engineering had focused on bolt technology precisely because it appeared more scientific, precise torque measurements, standardized threading, and installation procedures that could be documented in technical manuals. American rivet crews operated through accumulated expertise that couldn't be reduced to formulas, requiring years of apprenticeship to develop the hand-eye coordination and metallurgical intuition that made consistently perfect installations possible. By July, Bowser's system had achieved breakthrough momentum. 22 stories of structural steel were erected in 22 working days without overtime or night work, demonstrating that American industrial efficiency could operate at peak capacity while maintaining safety standards that European critics had claimed were incompatible with high-speed construction. Photographic documentation sent to engineering journals in Berlin and London showed installation rates that challenged fundamental assumptions about human limitations in construction work. The breakthrough extended beyond mere speed. Mohawk ironworkers from the Kanawaki Reserve, whose ancestors had worked on major bridge projects throughout the Northeast, brought traditional balance skills and fearlessness at extreme heights that amazed even veteran construction crews. These men didn't simply install rivets, they perfected an industrial art form that combined ancestral knowledge of working at dangerous heights with immigrant precision and American organizational innovation. McGrath's legendary skill at catching rivets blindfolded became more than mere showmanship. It demonstrated the level of hand-eye coordination that separated master craftsmen from ordinary laborers, proving that American construction success depended not on replacing human skill with machinery, but on amplifying traditional expertise through superior industrial organization. His ability to judge the perfect trajectory of a 1,700-degree projectile thrown 25 feet through open air represented the pinnacle of manual precision that European bolt installation could never duplicate. The human element distinguished American hot rivet technology from European alternatives. While bolts could be installed by workers with minimal training following standardized procedures, rivet crews required years of experience to develop the split-second timing and metallurgical judgment that made perfect connections routine. This expertise couldn't be imported or learned from textbooks. It emerged from the unique American combination of immigrant craftsmanship, industrial opportunity, and the willingness to attempt techniques that traditional engineering considered reckless experimentation. The transformation became undeniable by late July, when Heinrich Müller received photographs that challenged everything he understood about structural engineering limits. 22 stories of Empire State steel had risen in exactly 22 working days, documented with time-stamped images that European observers initially dismissed as American propaganda. Muller studied each photograph through his magnifying glass, searching for evidence of compromised workmanship or safety violations that would explain installation rates his calculations deemed impossible. What the photographs revealed contradicted fundamental European assumptions about the relationship between speed and quality in major construction. American rivet crews were achieving 12 connections per man per day, not through reckless haste, but through systematic perfection of technique. Each joint showed the characteristic mushroom head that indicated proper installation, with no evidence of the stress fractures or incomplete penetration that European engineers predicted would result from accelerated construction schedules. The critical discovery that validated American methods came through metallurgical analysis of completed connections. Hot-driven rivets completely filled their designated holes as they cooled and contracted, creating bearing contact across 100% of the joint surface. Modern European bolts required oversized holes with clearance gaps to accommodate manufacturing tolerances, introducing microscopic play that allowed gradual loosening under the constant vibration and thermal cycling that affected tall buildings. William Starrett commissioned independent testing of rivet connections from the building's lower floors, where installation had been completed weeks earlier. The results vindicated his faith in hot rivet technology. Laboratory analysis revealed that cooling rivets had generated clamping forces exceeding 30,000 pounds per connection, squeezing steel plates together with molecular-level intimacy that bolted joints could never achieve. The thermal contraction process had essentially welded the connections while maintaining the ductility that allowed structural flexibility during wind loading. European bolt manufacturers, sensing their technological superiority challenged, flooded engineering journals with technical papers emphasizing the scientific advantages of their standardized systems. German steel companies offered detailed calculations proving that modern high-strength bolts, installed with calibrated torque wrenches, provided more reliable and measurable connection strength than what they characterized as primitive American hammering methods. The human element driving American success became legendary throughout Manhattan's construction community. Pat McGrath's reputation extended beyond mere technical skill into the realm of industrial artistry. His ability to catch red-hot rivets while suspended on narrow steel beams 800 feet above Fifth Avenue represented the marriage of immigrant determination and American opportunity that transformed manual labor into skilled performance. Construction crews from competing projects gathered during lunch breaks to watch McGrath demonstrate his blindfolded catching technique, recognizing they were witnessing the perfection of a uniquely American industrial art form. Carlo Benedetto's mastery of metallurgical timing achieved similar legendary status. His ability to judge optimal rivet temperature through visual assessment exceeded the accuracy of expensive scientific instruments, rejecting pieces that deviated by as little as 50 degrees from the 1700-degree target. This expertise represented generations of Italian metalworking knowledge adapted to American industrial scale and speed, proving that immigrant craftsmanship could elevate mechanical processes into precision arts. The Mohawk ironworkers from Kanawake brought ancestral skills that amazed even veteran construction crews. Their supernatural balance and fearlessness at extreme heights, developed through generations of high steel bridge work, enabled installation techniques that European safety regulations prohibited. These men didn't merely complete their assigned tasks, they pioneered working methods that maximized both efficiency and safety through intuitive understanding of structural behavior at dangerous elevations. By August, European engineering criticism had evolved from dismissive skepticism to grudging recognition that American methods were achieving results their theoretical models couldn't explain. British engineering journals published grudging acknowledgments that Empire State construction rates exceeded anything achieved in European projects, though they maintained that such speed must compromise long-term structural integrity. The deeper significance of American success lay in its demonstration that industrial innovation could emerge from practical experience rather than academic theory. European engineering education emphasized mathematical precision and controlled laboratory conditions, producing engineers like Muller who excelled at calculating theoretical limits, but struggled to envision possibilities beyond established parameters. American construction culture had developed differently, driven by immigrant workers willing to attempt techniques that formal engineering education considered unscientific. Starrett recognized that his crews were proving something larger than construction methodology. They were demonstrating that American industrial organization could achieve superior results through the systematic coordination of human expertise rather than mechanical standardization. European bolt technology represented the triumph of scientific measurement over craftsman intuition, while American rivet crews had perfected the opposite approach, elevating human skill through industrial coordination that amplified rather than replaced traditional expertise. The economic implications became apparent as construction costs remained within projected budgets, despite achieving installation rates that European estimates claimed would require substantial overtime expenses. American efficiency emerged not from mechanization, but from optimizing human performance through superior organization and immigrant craftsman expertise that couldn't be duplicated in European workshops. Weather delays during late summer storms provided additional validation of American rivet superiority. While construction halted during dangerous conditions, completed connections showed no evidence of stress damage or loosening despite exposure to temperature variations and wind loading that European engineers predicted would compromise joint integrity. The thermal contraction that occurred during rivet cooling had created preloaded connections that actually strengthened under structural stress rather than weakening like bolted joints. The installation of the 500,000th rivet in early September marked a symbolic milestone that international engineering observers could no longer dismiss as temporary American success. Project documentation showed consistent quality across hundreds of thousands of individual connections, proving that hot rivet technology represented systematic industrial capability rather than occasional achievement by exceptional workers. The derrick crane collapsed at 11:47 on the morning of September 15th, sending 2 tons of twisted steel crashing through the 67th floor framework with a sound that echoed across Manhattan like artillery fire. John Bowser was inspecting rivet installations 3 floors below when the impact shook the entire structure, followed by the terrible silence that construction workers recognize as the aftermath of catastrophic failure. 3 men died instantly: Irish steelworker Timothy O'Malley, Italian crane operator Giuseppe Torino, and Mohawk ironworker Joseph Beauvais, their bodies crushed beneath machinery that had been lifting structural beams into position just moments earlier. Within minutes, the construction site transformed from organized industrial activity into emergency evacuation as Bowser ordered all workers off the upper floors pending investigation. The crane failure had destroyed 2 days of completed steel erection and created a debris field that made the 67th floor impassable, effectively halting vertical construction at the project's most critical phase. Police cordoned off Fifth Avenue for 3 blocks as fragments of twisted metal continued falling from the damaged structure, while newspaper photographers captured images that would dominate front pages throughout America and Europe. Heinrich Müller arrived at the site within hours, accompanied by insurance investigators and city building inspectors whose authority to shut down the entire project hung over every conversation. The German engineer examined the wreckage with methodical precision, documenting failure points and stress patterns that would determine whether American construction methods had finally exceeded safety limits. His preliminary assessment focused not on the rivet connections, which had remained intact despite the catastrophic impact, but on the crane's mechanical systems and installation procedures that European safety protocols would have flagged as inadequate. European engineering experts descended on Manhattan like carrion birds sensing opportunity. Representatives from German steel companies, British construction firms, and Swiss precision manufacturing corporations arrived with technical documentation proving that modern bolt technology offered superior safety and reliability compared to what they characterized as primitive American hammering methods. The tragedy provided perfect vindication for their long-standing criticism that American construction speed inevitably compromised worker safety and structural integrity. The deeper problem extended beyond mechanical failure into fundamental questions about American industrial methods. Modern bolt manufacturers, recognizing their opportunity, flooded engineering journals with advertisements emphasizing scientific precision and controllable installation procedures that eliminated the human variables they claimed made rivet work inherently dangerous. German companies offered to supply complete, bolted connection systems that could be installed by workers with minimal training, contrasting their standardized approach with American reliance on immigrant craftsman expertise that they portrayed as unreliable and unsafe. Carnegie Steel faced enormous pressure from European partners who demanded immediate abandonment of hot rivet technology in favor of scientifically superior bolted systems. Corporate executives, despite their material supply contracts with the Empire State Project, privately calculated the reputational damage that project failure would inflict on American construction methods throughout the international engineering community. The financial stakes extended beyond single building construction into America's credibility as an industrial innovator capable of competing with European technological sophistication. New York City building inspectors, responding to intense political pressure and European engineering criticism, implemented additional safety requirements that threatened to slow construction progress indefinitely. Every rivet connection above the 50th floor would require individual inspection and documentation, while all crane operations would be subject to European-style safety protocols that prioritize theoretical risk mitigation over practical efficiency. The regulatory response effectively validated European claims that American construction methods were inherently reckless and required external oversight to prevent future tragedies. William Sterrett faced the most difficult decision of his professional career. Abandoning hot rivet technology would save the project's immediate timeline while acknowledging European engineering superiority, but it would also invalidate everything American construction had achieved through decades of innovation and immigrant expertise. Continuing with rivet installation despite the tragedy would require proving that American methods could deliver both unprecedented speed and absolute safety, a combination that European critics claimed was physically impossible. The investigation revealed that crane failure resulted from mechanical defects in European manufactured lifting equipment rather than problems with American construction methods. But European engineers used the tragedy to attack the entire hot rivet approach. They argued that the accident demonstrated the inherent dangers of American haste and the need for European-style systematic safety procedures that prioritize controlled conditions over installation speed. Bowser spent 3 days conducting comprehensive analysis of every rivet connection in the completed structure, organizing visual inspection, stress testing, and metallurgical evaluation of joints that had been installed over the previous 4 months. The results provided overwhelming vindication for American methods, Not a single rivet failure appeared anywhere in the structure. Every connection maintained perfect structural integrity despite the catastrophic impact that had destroyed the crane and surrounding framework. The hot-driven rivets had performed exactly as Starrett predicted, providing connection strength that exceeded European bolt technology under the most extreme stress conditions. The tragedy became a rallying point rather than a defeat when preliminary investigation results reached the construction crews. Workers who had witnessed 3 colleagues die in service of American industrial innovation returned to their posts with renewed determination to prove that their methods represented progress rather than reckless experimentation. Pat McGrath resumed his legendary rivet-catching demonstrations with increased precision, while Carlo Benedetto's temperature judgments became even more exacting as the entire project community recognized they were defending American construction credibility against international criticism. Alfred Smith, speaking at the memorial service for the 3 dead workers, transformed personal tragedy into national mission. The former New York governor declared that completing the Empire State Building with hot rivet technology would honor the sacrifice of men who died advancing American industrial capability. Abandoning their methods would betray not just the deceased workers, but the immigrant communities whose expertise had made American construction superior to European alternatives. Enhanced safety protocols emerged from the tragedy without abandoning fundamental American approaches. Bowser implemented additional crane inspection procedures and expanded safety training while maintaining the rivet installation rates that had made the project legendary. The crisis had tested American resolve and validated American methods, setting the stage for a construction comeback that would definitively prove hot rivet superiority over European bolt technology. October brought a transformation in both weather and resolve as William Starrett stood on the reconstructed 67th floor, watching his crews achieve installation rates that defied every prediction Heinrich Müller had made 6 months earlier. The tragedy had galvanized American determination rather than breaking it, creating a unified purpose that elevated individual craftsmanship into collective mission. John Bowser's enhanced safety protocols operated seamlessly alongside the rivet installation system that had made the project legendary, proving that American innovation could achieve both unprecedented speed and absolute worker protection. The comeback manifested in numbers that European engineering journals initially refused to publish. November installation records showed 14 rivets per man per day, sustained across 43 separate 4-man crews working simultaneously on different floors. The mathematical impossibility that Müller had declared in March had become routine operational reality through the systematic perfection of techniques that transformed immigrant expertise into industrial supremacy. Pat McGrath's crews alone installed over 2,000 rivets per week, while maintaining the precision that made his blindfolded demonstrations legendary throughout Manhattan's construction community. December weather tested American resolve with temperatures that dropped below 20 degrees Fahrenheit and wind conditions that European safety protocols would have halted construction for weeks. Instead, Bowser's crews adapted their forge operations to maintain 1,700-degree rivet temperature despite Arctic conditions, proving that American industrial innovation could overcome environmental challenges that European engineering considered insurmountable. Carlo Benedetto's ability to judge optimal installation timing became even more critical as cold weather affected steel thermal properties, requiring metallurgical expertise that no European technical manual could codify. The winter months revealed the superior performance characteristics that distinguished hot rivet technology from European alternatives. As temperatures dropped, the thermal contraction differential between hot rivets and cold structural steel increased the clamping force generated by each connection, creating joint strength that actually improved during the harshest weather conditions. European bolt systems performed oppositely, with cold temperatures reducing the effectiveness of threaded connections and creating microscopic gaps that allowed gradual loosening under wind loading. International recognition came grudgingly, but definitively, as European engineering delegations arrived to document American techniques they could no longer dismiss as temporary success. British structural engineers, German steel manufacturing representatives, and Swiss precision instrument makers conducted detailed analysis of rivet connections from various building levels, searching for evidence of compromised quality that would validate their criticism. Instead, they discovered joint integrity that exceeded their most optimistic projections for bolt technology, with connection strength that had increased rather than decreased over months of service under extreme loading conditions. The installation of the final golden rivet on April 11th became a ceremony that symbolized American industrial triumph over European skepticism. Former Governor Alfred Smith personally drove home the ceremonial connection using the same pneumatic hammer that had installed over 1.5 million previous rivets, completing the structural phase 12 days ahead of the schedule that Heinrich Miller had declared impossible. The golden rivet, specially manufactured by Carnegie Steel, represented not just project completion, but vindication of American construction methods against international criticism. The final numbers silenced European engineering opposition through overwhelming empirical evidence. 1,575,100 rivets installed. During 6 months of steel erection, completed in 410 total construction days versus the 547 days originally scheduled. The structural stiffness measurements revealed building rigidity of 42 pounds per square foot compared to 26 pounds per square foot for modern bolted construction, proving that hot rivet technology created superior structural performance through methods European engineering had dismissed as primitive. Zero rivet failures occurred throughout the construction process, despite installation under conditions that European safety protocols prohibited. The accident investigation had definitively established that the September crane collapse resulted from mechanical defects in European manufactured lifting equipment rather than problems with American rivet installation methods. Every connection maintained perfect structural integrity under stress loads that exceeded design specifications, validating William Sterrett's faith in immigrant craftsman expertise elevated through American industrial organization. Heinrich Müller's final report acknowledged what European engineering pride had prevented him from admitting 6 months earlier. American hot rivet technology had achieved results that traditional European calculations deemed impossible through the systematic coordination of human expertise that transcended mechanical standardization. His recommendation that German steel companies study American methods represented a fundamental reversal of the technological superiority that European engineering had assumed for decades. The Empire State Building's completion marked the apex of hot rivet technology, demonstrating that American industrial innovation could create structural connections superior to any European alternative. The building's rigidity, strength, and long-term durability would prove American methods definitively, but the broader transformation had already occurred. European engineering establishment had been forced to acknowledge that American construction represented evolution rather than crude experimentation, validating immigrant expertise in industrial organization over academic theory and controlled laboratory conditions. The human cost of American success extended beyond the 3 workers who died in September. Hundreds of immigrant craftsmen had risked their lives proving that American opportunity could elevate traditional skills into industrial artistry. Pat McGrath's legendary catching ability, Carlo Benedetto's metallurgical intuition, and the Mohawk ironworkers' fearless precision had combined to create construction capabilities that European methods could not duplicate. Their expertise represented the marriage of Old World craftsmanship and New World innovation that distinguished American industrial culture from European alternatives. The economic vindication came through cost analysis that proved American methods achieved superior results within projected budgets. European critics had predicted that American construction speed would require expensive overtime labor and compromise safety measures that would ultimately exceed traditional construction costs. Instead, the systematic coordination that Bowser had perfected enabled peak efficiency without premium wages, demonstrating that American industrial organization could optimize human performance through superior management rather than mechanical replacement of skilled labor.